No, you didn't catch that.
Mention it. So let me start off with something here. Keep going. So suppose B1, B2, all the way up to BK is a linearly independent set of vectors, all of which live in R. By the way, before I continue with the punchline of the theorem, what does that mean about the relationship? If I'm telling you right out of the door that these are linearly independent and they live in Rn, what's the relationship between K and N? Yeah.
I love the question
I am curious. I'll get back to that. Yes,
K is less than or equal to N.
that's right. K has to be no more than N, right? Because you can think about that, putting those vectors B1 up to BK in a matrix, for them to be linearly independent, every one of those has to be a pivot column, right? So you can't ever have more columns than you have rows, right? And what did you think?
I was gonna say they're a subspace Rn.
Oh, right. I mean, yeah, if you look at these vectors right here and just look at what they span, that will certainly be a subspace of Rn. If X equals C1, B1, C2, B2. That is to say, X is in the span of these vectors. Are uniquely determined. Okay, so what's the punchline of this? The punchline is, if you can write a vector in terms of a linearly independent set by choosing constants, C1, C2, that make up, choosing weights as your book calls them, that makes that vector X, then there's only one choice for those CIs. And I'm gonna leave see if you can figure out why that's true. So in particular, so if H is a subspace from Rn and B1, B2, BK is a basis for S, then every element of S, that is every vector that lives in this subspace, is a linear combination of B1 up to BK right? That's what it means to span it, right? So what does a basis do? It does two things. It spans the space. So everything in space is a linear combination of them, right? And what else is true about a basis? What's the other qualification that you need for the vector to be a basis? So everything needs to be written as a linear combination of the basis, but the basis is efficient. It's small. In what sense? What has to be true of the basis? Yeah, that's right. If you put them in the matrix, pivot column. But let me put it this way: the basis is
they all have to be linearly.
they have to. It has to be a linearly independent set, right? and this gives this. It's uniquely a combination, right? So, let me give you a basis it's easy to see, and a subspace it's easy to see. So I'm gonna look at R3 and I'm gonna ask you, can anybody think of a basis of R3? Yeah,
100 and 010 and 010. Okay, then.
I like that. That's the easiest basis. Remember this notation here. 100, 010, and 001. You can check a couple ways that this is actually a linearly independent set. I'm going to do it sort of from the definition way. What does it mean to be linearly independent? What it means to be linearly independent is if a linear combination of these vectors add up to the zero vector, what should I be able to say if they're linearly independent? A and B and C all have to be zero. You're forced, right? That's what it means to be linearly independent. Let's see how this works out for us, shall it? Would everybody agree that I can collapse this side, the vector A, B, C? And that should be what? 0, 0, 0?
Yep.
And now just play math game, baby. A is 0, B is 0, C is 0. There you go. That's a linearly independent set that was given, right? Here's another way, for those of you that are big matrix fans, what happens if you put those three vectors I gave you into a matrix? You get the identity matrix, right? All of them are pivot columns. It has to be linearly independent. Agreed? And does it span? What does it mean to span? It means that any vector in R3, you need to be able to express it as a linear combination of those three vectors, right? What's my favorite vector in R3? So A, B, C, and R3. I have to be able to write that as a linear combination of it. And how do I do it? Fill the blanks. What can I fill in the blanks? Make this be A, B, C. And there you go. So linearly independent spans its basis for. There are other bases. Is that a basis for R3? Ooh, it's a little harder to tell, isn't it? let me ask you a question. If you put this into a matrix here. How many pivot columns I got? I had 3 pivot columns, right? Right? So that means that this set is linearly independent. Okay, check. First check. Second question, these 3 vectors span all of our 3. They do, how do you know? Is there a quick way to tell?
You can run.
I think he's right. You can row reduce it to the active, right? Everybody agree with that? Anyway, here's another way to see it though. Every column's a pivot column, right? Doesn't that mean there's a pivot in every row since it's square matrix? Since there's a pivot in every row, the columns must span all of R3. So this is both a linearly independent set and it spans, right? Would everybody agree this is an easier basis to see what's going on, right? But this was a basis nonetheless too. Why would I care about any? Well, it depends on your problem, right? A good example, although this is a little like linear algebra attack, how many of you have ever done polar coordinates before? Right? Why would you care to change coordinates or do a different basis? Because sometimes it makes your problem easier. Take this circle here. What's the area? Have you ever had to figure out the area of a circle by integrating it? It's obnoxious, isn't it? The first problem is this isn't even a function, right? So you've got to solve for y. Y is the square root of 1 minus x squared. You've got to isolate the upper half because that's the function part or by the one you want. You do some crazy integral, then you double it, right? Does anybody know what the equation of this is in polar coordinates? R equals 1. This is easy to integrate, right? And that's the value. It turns Cartesian coordinates are very good at dealing with straight sides, squares, lines, things like this. Polar is much better at dealing with things that are circular, things that involve sines and cosines. So sometimes you might want a different basis than the one you're given because of the particular problem you're working on. And I'll hopefully give you another example of that in a moment. Let me give you a definition. We can have, as we've seen, we can have many bases for any given subspace of Rn. So let me give you a definition here. Let S in Rn be a subspace. And fancy B, a collection of vectors a basis. So what do I know about this collection of vectors B1 up to Bk? I know that everything in S is a linear combination of this, and I also know that this is a linearly independent set. Now, this is a definition. So what am I defining? I'm defining what's known as the B coordinates. If X is any vector in S, so take any vector X and S, then X is uniquely a linear combination of elements to B, the vectors in B, lambda 1 B1 plus lambda 2 B2 lambda K. Then We say lambda one, lambda two, lambda k are the coordinates of x relative to the basis. So in other words, what the coordinates are in order. They're just the numbers that you need to make that linear combination be x. Right? And I'll show you how that connects to terminology you're probably used to. Sometimes we write so read this, the vector x with coordinates in B is lambda one, lambda two, the lambda k. So these are the B coordinates of lambda one up to lambda k, B coordinates is vector x. Let me ask y'all something from your experience, from your past travels. When the word coordinate comes out of my mouth, what do you think of? You probably think of a point in the XY plane, right? Give me some coordinates, right? 2, 5. You know where that is, right? This is exactly. So if I were to graph, let's say point 2, 5, and I'll write like a vector. Wouldn't this be like 1, 2 over and 1, 2, 3, 4, 5 high, like that? Right, this is 2 in the standard coordinates. Or I'm sorry, this is the regular coordinates are coordinates in terms of the easy basis 1, 0, 0, 1. Right? That's where coordinates come. But we can do coordinates in terms of any basis. Right? So here we go. 2 of these, 5 of these, and that gives me coordinates. Right? Let me give you another basis. Let's let B equal 1, 1, 1 minus 1. So if that's basis. By the way, this is probably less of an obvious basis, but put that in a matrix and see that that does indeed row reduce the identity. This is a linearly independent set, and it spans all of our two. So if XB is equal to, give me two numbers. You can give me 2.
7, 13.
7 and 13. Find the X and standard. So this is just kind of an exercise in what this notation means. What does X be? It means in B coordinates, weight 7, weight 13. So X is actually so in the standard coordinates we're used to, what do we get?
I think 20 negative 6.
That's right. So it's just 7 of these plus 13 of these gives you a grand total of, in standard coordinates, 20 minus 6. Okay, let's reverse this. Another linear algebra problem. Here's another example. What is 2, 5? You already did this one, right? That's in standard coordinates. I know where that is. Over x2 up to y5. What is that in terms of the basis? How do we find that? How do we find that? Terms of basis?
So matrix.
That's right. We can kind of do that. Let's reverse engineer what we did before. Let me write the basis here. Well, it should be A becomes 1, 1 plus B becomes 1 minus 1. And this should output to 2, 5. Everybody agree with that? I need this many 1, 1s, this many 1 minus 1s to get me 2, 5. And as you predicted, this is going to be a matrix, right? This is just a system of equations. So in fact, what you get is you get A plus B. I can do it very quickly this way. A plus B must be 2, and A minus B is equal to 5. Correct? So let's see what we get. 2A 7. So A 7 halves, and B is like what, minus 3 halves? Yeah, that's what it is. So you can write 2, 5 standard as 7 halves times the basis of this minus 3 halves. And actually, you could check it if you had a ruler and all that sort of thing. Just take 1, 1 times 7 halves, 3½ of these, and then minus 1, 1 minus 3 halves times, and we'll find these out. Any questions on this? Let's do one more of these. Let H equals span of a couple of vectors here. What do I got? 1 minus 1, 2, and 3, 2 minus 1. By the way, is it possible that these two vectors span all R3? No way, right? Everybody agree with me? Because these two vectors are linearly independent. You can check it if you make the matrix. If you make the matrix out of these two vectors, they will both be pivot. They'll both be pivot columns. However, it's impossible for there to be a pivot in every row, right? Because there's only 2 columns in there's 3 rows, right? So it's impossible for them to span. No surprise here. And this is a subspace of R3. And my question here is find if V is vectors that I'm expanding. Find V coordinates. Right here, 11, 4. By the way, let me ask you all a question, just from my teaching perspective, right? I make up these examples for your all's enlightenment or whatever. If I just make up those three numbers, 11, 4, 1, what's a big potential problem for me? So we got these two vectors here. What if I just put in three random numbers here? What do you think it's likely to happen?
It's not solid.
That's what I would guess, right? Because these are two vectors in three-dimensional space. They should make a plane. If I pick three numbers at random, what are the chances that it's going to be on that plane? Almost zero, you would think, right? So I probably made this example up first because if I pick these at random, it's probably not going to be. There's probably going to be no B coordinates because it may not even be in B. We'll see what happens. We're solving once again with the themes again, the augmented matrix. 1 minus 1, 2, 3, 2 minus 1, 11, 4, and 1. Better get a row of zeros here. Wow. Okay, so I'm going to use first row, that one up there, to take everybody out. So I'm just going to straight up add 1, 3, 11, 0, 5, 15, I guess. And I'm going to multiply this by minus 2, take that out, and get 0, minus 7, minus 22, and 1 is minus 21. Groovy so far? What's my next move in this chess game? I'm going to divide the crap out of these last two lines. So this is going to be 1, 3, 11, 0, 1, 3, 0, 1, 3. Well, how about that? This is 1, 3, 11, 0, 1, 3. So what do we get? We get that it's consistent. Everybody agree with it? So since it's consistent, that means that yes, this thing is in the span. There is a solution. Interpretation, what is my solution? This equation is what? X2 is 3. And this one is X1 plus 3X2 is 11. Ooh, even I can solve that. And if X2 is 3, so here are my coordinates. So the coordinates for this vector 11, 4, 1 are in order 2 and 3. So in this case are 2. So in other words, 2 times this one. And here's another great thing about checking these questions. You can always check yourself. Always, always, always. Go back and see if this makes sense. 2 times this one plus 3 times this one. It better give you the 11, 4, 1. 2 times 3, that's going to be 11. 2 to 3, that's going to be 6 minus 2 is 4. This will be 4 minus 3 is 1. Fantastic. Everybody okay? Any questions? Let me give you an example. By the way, I did flippantly say at some point that the span of these two vectors defines a plane, right? Some of you were asking about this last time, right? You have two linearly independent vectors, and somebody said, "Is this the same as R2?" Well, I'm gonna give you a definition. It's not the same as R2, because notice this is a subspace of R3, and all these vectors have 3 coordinates. So this actually lives in R3, but it is sort of the same as R2 in the following sense. Definition. A linear transformation let's say L from, let's say S, well, no, it's S 1 to S2. S1 is a subspace in S2 a subspace of Rn. Is an isomorphism is 1-to-1 and on. So in other words, the vectors from here to here are paired off. It's 1-to-1 and onto. Everything's covered, and no two different ones go to the same thing. In this case, we say S1 and S2 are isomorphic. Isomorphic is a word used in mathematics that means maybe not equal. They could be maybe not equal, but for all intents and purposes, the same thing, right? Let me give you kind of a little exercise to think about. Let me read on this example that I had here. 1 minus 1, 2, and 3, 2 minus 1. So take this first basis factor and just force it to go there. Take the second basis factor and force it to go there, right? So I'll tell you exactly what this linear transformation looks like. Everybody remember that anything in H, the span of those two vectors is a linear combination of those vectors, right? Right, good with that? So let me tell you what the linear transformation does. This is what a garden variety element of the span of those two vectors looks like. It's something times the first one plus something times the second one, right? This is a linear transformation, so I can tell you exactly where this goes. This goes to A and this is A times 1, 0 plus B times 0, 1. This goes to AB. So these are the B coordinates, and they just go to the standard coordinates in R2. It's easy to check that this is 1 to 1. You might have to check it, right? And it's clearly onto, because given any AB here, just take A times this and B times this. That's where it'll go. This is one of the cool things about linear transformations. Is all you have to do is tell the basis where to go, and that tells you exactly what the linear transformation is. And so, in other words, so to answer some of the discussion that we had last time, this weirdo plane sits somewhere in three-dimensional space. I'm not even sure what this thing looks like, but it's some plane that sits at some funny angle in free space, is essentially the same as R2, right? Because R2 itself is. Okay. Any questions? I am going to give you some more definitions here that we'll need to know in the sample. Definition. Let H be a subspace. I've thrown this word around really loosely. I'm gonna make it a little bit more precise. Dimension of H is the number of vectors in any basis of H. And I'm gonna add one more technical caveat to this in a moment. But if you have, so I'm glossing over something that's important here, but you can take this, at least for now, as a matter of fact. If you have any vector space, it has a basis. We've mentioned this before, right? So any subspace will have a basis. It's a maximal linearly independent set. It's a linearly independent set that spans it. One of the things implicit in this is if you have a subspace of Rn, and you've got one basis, and maybe you've got another basis, another, all of those bases that you find have the same number of vectors in them. Right? You can't have a basis of 3 vectors and the same space have another basis of 2 vectors. It's always the same number. And this is a fact. My caveat here is if H equals 0, then dim H is 0. The 0 vector space has the empty spaces. There's nothing in the 0 space that's linearly independent. So when I say dimension, I mean the size of the basis, and it's any basis because they all have the same size. Definition, here's another one. Let A, and you guys are going to help me come up with a theorem here. Let A be any n by n matrix that you the rank of A is when I say the rank of A, what I mean by that is look at the column space and look at the dimension of that. So the rank is the dimension of the column space. Here's another way to prove it. What's another way? So those of you that are computationally minded want to figure this out. What's another way? What is the dimension of the column space? is actually the number of pivot columns. Right? And this will help with our theory. So if I have an n by n matrix, if you hear me say the rank, what I'm doing is, what the rank means is it's the dimension of the column space, which is the same as the number of pivot columns. Let me ask you a question. Same notation, I've got an n by n matrix. Wait, tell me what the dimension of the null space is. Remember, the null space is the solution to AX equals 0. When you look at the homogeneous equation, AX equals 0, how do you tell what the dimension of that is?
The number of free columns.
The number of free variables, right? Everybody agree with that? So we looked at that last time. Whenever we're computing the null space, the number of free variables is the number of parameters. It's the dimension of the null space, right? Everybody okay with that? So this is number of, what's the number of free variables? That's the same thing as the number of non-pivot columns, right? Everybody agree with that? Now, I don't know much, but the number of pivot columns plus the number of non-pivot columns should add up to the number of columns. So this should be n, the number of columns, minus number of pivot columns. And that brings us to what is known as Rank-Nullity Theorem. If A is matrix m by n, then rank of A, which is the number of pivot columns, plus dimension of the null space of A, which is the number of non-pivot columns, should equal the total number of columns. And there you go.
Yes.
Yeah.
Why is the number of, or why does the dimension of the columns get its own function?
What's it now? What is the?
So like dimension of the column of A gets its own function rank, but dimension of the null of A is nothing.
Oh, so really, so the question is why is the dimension of the column given the title rank, right? Well, you're going to see, because actually it turns out that the rank of A and the rank of A transpose are the same. And so, and it actually doesn't matter. So people just kind of think going from columns first. You can do this in terms of rows, and actually some people do matrices backwards. But yeah, I mean that is kind of strange. But the null space actually has its own terminology that's considered important in other walks of this as well. So let me give you a theorem here, and this is useful as well. Let's let S be a k-dimensional subspace of R. could be Rn itself, but any k-dimensional subspace of Rn. Then any linearly independent set of k vectors of S is a basis. So that's kind of cool thing, number one. If you know at the outset, if you know that the subspace is k-dimensional, and you go like picking up seashells and find k linearly independent vectors in there, it's automatically a basis, right? Any k linearly independent vectors in a k-dimensional subspace is automatically a basis. And there's also another one, and that is also any k vectors, exactly k vectors, that span S is the basis. So if you have exactly k vectors in a k-dimensional vector space or a k-dimensional subspace that span it, then that set automatically has to be linearly independent. If it's exactly k, no more than k, that would be linearly independent on the basis of that subspace. Okay. Any questions so far? I'm going to give you one last thing before you go, and this is just really a theorem that ties everything together and connects with what we have before. So there's really kind of nothing new here, but this is kind of good for your notes. Theorem. So this is more equivalent conditions for a matrix to be invertible. Let A. Okay, pay attention to that because n by n, we're square matrix here. The following are equivalent. So these are all, as I talked about earlier, these different perhaps sounding statements are all equivalent statements. They're all logically equivalent. A is invertible. 2, the column space of A is all of Rn. Number 3, this is kind of silly, but I'm going to do it anyway. Columns of A are a basis for Rn. Number 4, the dimension of the column space of A is n. Right, no surprises there either, I don't think. 5, rank A is equal to n. And David might want to complain about this because this is the same thing, right? This is just terminology, right? And 6, the null space of A is 0 vector, and 7, the dimension of the null space of A is equal to 0. And that's that. Okay. Any questions on that? All right. Well, if you got an interest in numbers, come to the math club. Other than that, y'all have a good weekend, and remember to mark the calendar for the new session on Monday.